So we will start the second session of this afternoon. This morning and this afternoon we have seen the Souriau model of Lie group thermodynamic, and this Ifology is also invention of Jean-Marie Souriau. And so I was very happy when I discovered that Hong Van Lee has used this tool for extending Fisher metric. So Professor Hong Van Lee will give a talk on Diffological Fisher metric.
Thank you very much. Yeah. It's my pleasure to be here in the beautiful place to give a talk on Ecological Fisher metric, and its source is coming from information geometry and dynamical system of invented. The notion of Diffology is invented by Professor Souriau. Okay, so that's what is a Diffological Fisher metric? It is a natural generalization of Fisher metric from the case defined on the parameterized statistical model to Diffological statistical model. It is a statistical model endowed with Diffology, and in particular, any parameterized statistical model in the sense of the information geometry is a Diffological statistical model. And in my talk, I shall discuss some property of Diffological Fisher metric, in particular the so-called Diffological version of the grammar round inequality. So the plan of my talk is divided in the 4 parts. First, I discuss about the intrinsic Riemannian metric on statistical model. Intrinsic, that means it does not depend on any parameterization. And then I discuss the notion of Diffological statistical model is a combination of the Diffological space, invented by Souriau and Houches, and the notion of statistical model. So how to combine these two notions. And then that is, once you understand what means that the intrinsic Riemann metric on statistical model and Diffological statistical model, the notion of Diffological Fisher metric is come very natural, present. And then I shall discuss the Diffological grammar inequality. Okay, so that's according to currently accepted notion among statisticians. A statistical model, I mean that's not among information geometry, but among statisticians, a statistical model is a subset of the set of P probability measure on X is only I consider that measure space, so I have to say miss out the space of the sigma algebra here. So that's a measurable space. So X is only measurable space. So so that means that statistical model can be very singular, any subset, not necessarily smooth. And then, but nevertheless, it has any it is a subset of the set of on probability measure, and this probability measure is a subset of the on finite signed measure, S for signed measure. And this space of on finite signed measure is a Banach space. It's total variation for norm. And the Banach space is wonderful, geometry, because of that kind of natural generation of the from finite dimensional Riemann geometry to the case of Banach geometry. Of course, there are still a lot of problems if that's not in their space, but at least I just skip some question about what is the difficulty here. And then now forget that you consider the finite sign space on finite sign measure on measurement space X. I consider general Banach space denoted by V is Banach. I text it any norm here, and now I let's X is some subset of V, so I is embedding, and X naught is some point on x. So I denoted that is what a tangent vector. If this is a C1 map, so that is a here. You have space a V here. Any subset terrific like that. So x naught is x. So tangent vector is so that is if you have the map from R here, C will go to x, but that is x, then here's an embedded P. So you can consider that the I C is a map from R to V, right? And the target space, the Banach space, the domain is R. So there's the notion of the smooth map. Yes, so that's on smooth map, then I say that's okay, then you can define the tangent vector. So that is a tangent vector if there is a C on map, such that is a okay, I forgot here. Such that V equal C dot, yeah, of noon and of course C noon equal X noon. Okay. C on C here. So that's I'm sorry that I just missed this condition. Now then, denoted on this tangent vector fx is called that double tangent cone here. Say x is the arm of the v is tangent to x at x naught. So that means that even a subset is not have a smooth structure. You can define the notion of the tangent cone, right? That is just very kind of the standard structure in geometry. They know already a long time ago, and used also in algebraic geometry. Now the next thing is to so you have the only tangent cone because the thing is very bad, but that is you have some set like that. Then I define the notion of tangent space is a linear, how to say, the whole of the tangent cone, yeah, x is an already linear space. I call that that is a tangent space, and tangent fibration is a union of all these tangent space. So it can be have very different dimension. I can show the picture. The picture is the following. Now I consider because how to define subset, the best way is using some parameterization. And in this example, I use the parameterization by the easy kind of some density function. So and not is some reference measure. And that is nothing else like here is a mixture family. That means G1, Z2 is function, and one and the two is P eta is so that G1, Z2 is 3 is a given function, non-negative. Yeah. So G1, Z2 is some given function is a substrate condition. That's the expectation is equal 1. And now I take the parameterization is some specify as follows. I mean that's not necessarily very smooth thing that I take for example parameterization by on these closure of subset of these chest box, yeah. So that is a kind of a lot of corner here, yeah. So that's a little bit of the different from the classical setting in information geometry. That means parameterization domain can be very how to say a bit ugly, no? So and the same tangent is inside here is completely the two-dimensional. At this point, you have the only cone like that, yeah. So that you see immediately like that tangent space, tangent cone Of course, it's a different point. It's different, but if you take the tangent space, that means the linear whole, then it's the only how to say the whole space here, except of the yes. Yes, so it's only the whole space R2 here, but the tangent cone can be only where that's black here. Yeah. So that's the kind of the picture of the tangent space. But what is the different from the classical information geometry? Because in information geometry, what is important is a parameterization space, parameterized space. So all the geometry is defined on parameterized space. And then what I consider here is on geometry is on the space itself, so not the parameter. Yeah, so that is intrinsic. That means that you can have another parameterization here, and yes. So how is if the way how to get another parameterization is actually the concept of diffusion. Now, there's some questions. Yes, please. A checkbox is actually that's how to say that is a pattern recognition. Usually, how to make the recognition some part. Yeah, you make the checkbox. I make such a thing only, but you can take the for example any rule here. That actually, then you can make the yeah. So divide that is kind of the yeah. So I make checkbox. That means that how to make the to color some bar by some pixel. Yeah. So you can take the dot like that, and it has a parameterize a statistical model by this dot. Yeah. Okay. So now is let us to say something more about the tangent space. This thing is already know in our book, but actually already know before, not only in our book. So that's the fact I say here. So that's when you consider that is a property of the space of the measure. So now I consider a curve on here space of the measure. Yeah. So that's that. The curve in here that's on the space of the finite finite sign measure is a vector space. Yeah. And this is a kind of the park. Sometimes it's only the Amari says that sometimes better to consider the cone of the non-negative measure. So now what is the property of this curve on the time lying in the space of the probability measure or more general of the non-negative measure? The property is the following: any curve like in that, so smooth curve, then I denote this that it is CT, and V equal C up naught. Then the theorem is the following: not very hard, and not yet. Actually, if I want to cite it in our book, but it has been noted before that any vector tangent vector as a point here psi is a point in the probability measure or non-negative measure. It is dominated by C. And once it's denominated, you can apply Radon-Nikodym theorem, and it takes dv or dc is that's some function, yeah, and is a L1 function on the x, the c, and you call that is a logarithmic representation of the tangent vector. So from the v is a point in the px. So in the sx, generally V is some finite sign measure. But you take logarithm of it, then you have some function. So that a function is somehow kind of simpler, of course, than just consider some finite sign measure. And then you take the logarithmic representation of the cone of tangent vector is take a logarithm representation of each tangent vector. Then you have some subset in the space of the L1 function on X, yeah. And then is a definition. That's this now you have the subset here that Px. That's some subset that's statistical model inside of the space of finite sign measure. It's called as almost to integrable as a logarithmic representation of the any cone, tangent cone, is inside of the L2. Not and L2 is smaller, subset L1. And in this case, the Fisher metric can be defined as follows. For V and VW in the cone, I take the V of the scalar product is integration of the two function in the L2, and therefore you can take integration, right? That product of the two function in L2 is a function in L1. And then since Tx linear Houches, this formula extends uniquely to a positive quadratic form on the space of the X. It is called as a Fisher metric. Okay, so that is at the moment I only consider in a subset is the tangent space. So that's now I consider the notion of the diffusion statistical model. So that's what I define here depends strictly on the subset on the inside of the space of probability measure or more general non-negative measure, and does not depend on any parameterization. Now I consider the notion of diffusion statistical model. So that's also accepted among statisticians only since the very beginning. At least I read the paper of the Mark Stacksteder in '66. Yeah, they consider that parameterized statistical model is a parameter set together is mapping. Yeah. Theta to some theta to PC. But usually you want to parameterize by some nice things such as information. Geometry uses that theta is a Banach space or Banach manifold. Yeah? And the same therefore in our book you say that N is a Banach space and the parameterization such as a combination of the map parameterization is a inclusion to Banach space is a Sion map. Of course, it's a domain, the Banach space, and the target, the Banach space, so notion of Sion map is defined. Now, but there is something more than parameterize model in sense of our book is Nihat A. Jungenius and Lorenz Schwarzhofer. So you consider that as the simplest case, as the interval on 0 on is the Lebesgue measure. And you take the set of the dominated measure, so that you consider only density, and I take the positive density, and the claim that there does not exist Banach space such as Px is the set of here is parameterized by some Banach manifold. So people in functional analysis know because how to see assume the opposite. So you have some m map to the here Pm. Then of course the tangent of the m go to also tangent of the how to say, peak of the N here, yeah, right? And the tangent of and it's here the successive, then the maps on tangent map also successive, right? And then that means that the tangent of this map is nothing else of the function that's the integration. I forgot here that f, so is equal 0. But this is not the case since the space of smooth function cannot be the image of the linear bounded map from Banach space M2 and L1. That is no, no reason. I try to think that how about the marginal case, but I'm not very good at these techniques, so I have not yet able to extend the theorem more. Okay, so that means that if you only consider the Banach setting, that is it omits many important cases. And of course, now so I try to cover that even marginal case. I use the notion of the Diffusion. So Diffusion is introduced by Suryo, yeah. So what means that Diffusion? He of course you only discussed what importance that you consider some map from good domain to another thing. So usually in theory of the classical differential geometry, when you go from one domain to another domain, you want to think that transition map is invertible, but that it can be relaxed. And then how to relax? First, I mean that so that's the Sika Diffusion. So that means that you consider what is the Sika Diffusion. What means that on the smooth map, you define what means smooth map from N to Pn. Yeah. So definition is the following: covering contain on the constant function. On constant mapping is called smooth. Yeah, that belong to the Ifology. Locality is something like if smooth on this part and the smooth on the another domain, then smooth on the union. Yeah. And the smooth compatibility, that means if you change the domain from the U and V by some smooth map, not necessary, then you have the composition is also smooth. So that means that the definition is very simple. And then the notion of the Sika Diffusion space is that non-intercept equipped with the Sika Diffusion. So the best book is written by former student of Suryo. He was invited but cannot came. Ecological, so I advertise for his book. It's a really best book because before his book I read several papers on Ifology, but his book is the best. Now and then now that's now I come to the notion of the Diffusion statistical model. So so that means that when you have Diffusion, what the question is you have a statistical model, that means subset inside the space of finite measure. What is a compatible Diffusion? I say that the compatible Diffusion, that means that then you can search Diffusion statistical model if for that is the question I already talked from beginning. If this makes smooth, only how to say if for any I only that's not if and only if the compensation of the y here also smooth. Yeah. So if you have the statistical Diffusion, if you have the condition that the composition of the E in the smooth map, that means go to from the smooth domain to smooth target is a smooth in usual sense. And of course you smooth here, that means only to up order k, yes, because usually classical Diffusion they consider only C infinity, but in many part of information they consider C1. So I just put the CK. There are still many questions. What is different from K? So That's because the smooth case is completely has a much nicer property. So that's still many interesting questions to answer. Yes. Yes. I do not understand no, no, that's how to say. That's the diffology means that mean you what mean diffology? You diffology. That means each map from Rn to 6x are smooth. Yeah. So once you can define some subset, this set is a set of the on map. You just pick up and you want to claim such a complexity. So I should say you that I should give you more definition. So I do not understand that your question because you say you take some things that you tangent space. So the tangent, of course, that's the one you know that what is a smooth map, and I have not yet defined the notion of tangent cone. So that's once you know that what is a smooth curve, then you know that what is the tangent vector to that smooth. Yeah. So that means how to say the you the tangent cone of the diffology is smaller than of course, than the tangent cone I say from the beginning. Because from beginning I consider on possible smooth map, yeah. And diffology, that means that I just pick up some of these map. I claim that it is only these map are smooth. Is that okay? So now that the tangent space is a linear hole here. So that means that I choose some subset of the on smooth map. Yeah. Yes. Yeah. So the diffology is how to say diffology that you say that diffology not consider not smooth um, and when I mean that the thing is the following thing, okay? So that for example, I consider only I check have not yet checked, but that's a kind of momentous. So I claim that the C1 map is a takes only check fusion C infinity map, yeah. Okay. So it's that this is a space of C infinity. Uh, uh, you're not yet satisfied. So that is not good example. So that you can think that what is a smaller subset now of the I define the combination. I have not yet checked it, so but the thing is maybe only in Iglesias same book, yeah. He consider only on this infinity diffology, and maybe there are a lot of pathology example, and this case is only consider they concept indux diffology. That's in terms of the Iglesias Seymour. That's a diffology I define here as indux. I mean that's a subset of indux from the diffology. What I explained from the beginning, what is smooth math? That means it's in inclusion in the two is a smooth math that is called that indux diffology. Then you can take some subset of it. So okay, so let I check the book of Iglesias Seymour and the to find if he has some kind of the interesting example on your question. Now, if have now answer you, I only define the map in to n. What is smooth? Now I can answer. I define this, and I can define the what is the map out is smooth. If map out smooth, if you have the composition like that, yeah, from phi px to v composition of c to with the var phi is differentiable. Yeah, so depend only on the curve. Therefore, is only Gato differentiable. Yes, so the example here's a parameterized statistical, and this image of it is C1 differential statistical model. Dx consists of the on C1 map, such that there's a axis map. I mean that from go to UN and the composition of the Q is QN and the P here is Q is a composition P and QN. Yeah. So that is a natural Ifology. Yes, I consider K because how to say in the part of the book it considers C1 map. And in Ifology, till now they consider C infinity. So that's something that some people are more convenient. So I think that to be, how to say, cover on the case, you should consider CK. Of course, and then actually that's even in classical Ifology, they did not yet consider CK. Yeah? But the question, because how to say, even in the case of C infinity, there are many questions to be answered. Now the another example is any statistical model can be in the is the structure of the CK differential statistical model because I claim that on the mapping O e to Px is CK if the composition is embedding is a class CK, yeah, and because the target and the domain are Banach is a Banach space, and you can define what means that CK map, yeah. So that's now you say that's any best subset you think has defines the notion of CK differential constructive model. Now I go to the differential Fisher metric. That means that now what's the difference here? That's only the lobes of the cone. Tangent cone of the depend on Ifology is belong to N2, yeah. Then it's almost 2 integrable, and it's the concept 2 integrable is a function v to the absolute value of dpv. That dpv is some is a continuous on pu. U is parameterized map, yeah. So that's for any smooth map, this is a continuous, then the Fisher metric is called Ecological Fisher metric. That means that the point here is very important. That means that you replace C1 map by the continuous of derivative, yeah. It's more like a C1, yeah. So, but it's a very, in the sense of the pressure. That means you need only continuous of the on the tangent space, yeah. And then going back to the case of the parameterized statistical models, and XP is 2 integrable if and the only if that is the entity theorem, some theorem in our book. But of course here the reformulated. Because at that time, in that book, it doesn't have the notion of differential statistical model, but the theorem can be reformulated if the image of the parameterization and if the induced dn is a natural Ifology on n. So every smooth manifold has a natural Ifology what is the on movement, yeah, right? And that is a two integrable C1 different logical and statistical model. Uh, and here's a more interesting example, a little bit outside that we have not considered in our book. That is but that is considered by Thomas Friedrich. He wrote a very good paper on symplectic structure and physiometry, but in German in 91, and he considered not finite measure, but sigma finite measure. And that's a more case because Leber's measure on the R1 is not finite measure, but sigma finite measure, right? So that is a much natural case to consider the sigma finite measure. And he says P lambda is a set of the on Px that is dominated by lambda. And he defines the following Ifology. Of course, he used a different language. I translated it. Result, he says that the curve is the C1 curve is the logs of the how to say, tangent vector here is on space of L2. Yeah. So then, of course, that's a P lambda delta E2 almost integrable C1 diffeological statistical model. And then now what is interesting? So the what most interesting here that's related to information theory. I claim that the diffeological physiometric, like a physiometric, serve as an information quantity. It's respect to Markov-Kernen, but regarded as probability morphism. And then now here on the time of Markov-Kernen, it rise a three line of condition, and mapping from here to here is not mapping. Yeah, some function is a Markov-Kernen, but yes, for people in geometry, that analysis very good to consider n2 or map to n2 R. That to consider that Markov-Kernen, but people in geometry on something mapping from some space to some space, and that is a. And if you have very abstract setting, you can consider in category and probability morphism. And you already know that Chensov defines some kind of category approach, and he wrote the books, statistical diffusion rule and optimal inference using such categorical approach. But before that Lawware already proposed the categorical approach to probability theory, and when probability theory is statistics, two sides of the one thing, and you can apply to statistics. And in this theory, that's object are measurable space. Morphism is the Markov-Kernen. And the most beautiful thing that Lawware know and Chensov didn't know, that he says that if it puts the natural sigma algebra on space of on probability measure, then you can characterize Markov-Kernen in terms of the measurable mapping. So that so that I say that Markov-Kernen from X to I is nothing else as a measured mapping P from X to P of Y, and in there is some sigma algebra. VW. Okay, that's a long story. I put VW, but okay, that means that's a weak, yeah. Okay, that means that smallest sigma algebra suggests here's a kind of the linear function from mu to integration of f's to the mu for any f's simple function, and the mu in pitch is a measurable. So you want to have some kind of function is measurable. That construction very popular in topology. You have the notion of the initial topology, target topology, and now it changed by topology by measure. Is more or less the same thing, the same construction work here. And then you say that's okay. You define that sigma angular. Then he can say that's okay. The condition of the Markov covenant you write in terms of the several formula. I just write in terms of the measure mapping from X to space of probability measure is that sigma angular. And that's then on the formula of composition of the two Markov covenant is a Markov covenant you can write in terms of two very easily. You can look at our paper to see how it is. Of course, that's many people already know before, but we try to write some picture. Very nice. And then this case that is called probability morphism. Okay, so that's this. You have the following thing. So once you have T for Markov covenant from X to Y, but now you think in terms of morphism. And you can, once you have morphism like mapping, you have the induced, induced mapping on other associated structure. So the from X to Y, you have the space of the finite sign measure. And then you notice S is for S here, T is a mapping generated from the Sx to Sxy. But because I should not use any other functor like a Pt, Pe, so I should, my talk is only T star here for simplicity. And then T star apply to mu from X. B is some set in sigma angular, right? So because of that, that is the element from Y here, B is the element sigma angular here. So measure apply to, finite measure apply to some set is some number defined by integration here. So T bar here, X, you know that's a T bar here, the map from X to probability measure. So integration of X and the average per mu, then you got the number, yeah? Then what's observed on the by chance of that's a zip map move space of the probability measure to probability measure. So now the first claim that's why the Ifological statistical model is a natural thing in terms of the probability morphism because once you have probability morphism from X to Y, then you can transfer CK statistical model to apply mapping to CK statistical model. So T of the Px, you know that's a subset of the Py. The only thing that how to define the T star of the Mythology. So that now I define it here. A mapping from U to T of Px here, that is in the space of Y here, belong to T of dx, some Mythology I want to define here. If and only if that U is only open set in R and there exists some open neighborhood V of R such that either restriction of P on V is constant. You know that on constant map, smooth map. Or there success some mapping to dx such that P in V is a P star composition of the Q. So then that's the first theorem on this two integration CK Diffusion statistical model is that first that's a apply of is then apply of the two integration CK statistical models, and you also get almost two integration statistical model. Yeah, so that's a class of the almost integrated CK Diffusion statistical model is behave nicely under the probabilistic morphism. And then the second thing that is the Fisher metric is no how to say decrease under the probabilistic morphism. Is the equality only if that P is sufficient is respect to Px. So that means that's how to say. Usually that Markov covenant is a kind of the any information processing, and after information processing you get information done as a natural. So that's why I say that Fisher metric is quantify the information because more you apply the processing and lesser information you get it. And then now that's one of the important notions. That is what means that in static is a sufficient static, but now we extend it to the notion of sufficient probabilistic morphism. So it appears that only the Zach and Moss and Zach started only the think about it, and they define this notion. Of course, it's the kind of the category probabilistic morphism, but you can translate it in the definition in our language. That means that how to say, if there exists some inverse map, inverse probability morphism, inverse, that's not really inverse because you have map from x to py and another I to px. Yeah, inverse only when you write some curve arrow here. So I should not say that is the inverse, but in the in other direction. Such that for all the mu and h in the space of the bounded measured function on x, and you have the t applied to h mu because any bounded measured function multiplies to mu, you get some sign and finite measure, and you have the p of h and p and mu. In other words, p of h is belong to this, how to say, Radon-Nicodim derivative does not depend on mu, yeah, the function on h. So like a Fisher-Neyman condition, you have the family of mu, but you take the Radon-Nicodim derivative here, that actually that only depend on h here. And then in this case, you call that E P from Y to Px, the conditional mapping for T. And there's an example. Of course, that's since how to say, any statistic, how to say, mapping from X to Y, static, that means the measuring mapping from Y, defines a map from the, that claim if X to Y is a measuring mapping. How you define map from the X to Py? It's very easy. You have the Y to Py, that is a direct map, right? So you take the composition of the, here's a direct map. So that if here you have some measured by mapping, the composition is measured by mapping. And you can think easily that Markov kernel that you can define in this way. Yes, so I say that's how to say. I always say I was a very abstract Markov kernel, and I say that from X to Y, that means that's a measuring mapping from X to Py. So I also think that's how to say. I say that any measuring mapping that in statistics they call that the statistic. The static is also probabilistic mapping because I can define the measuring mapping from X to Py by composing it's a map from Y to Py, and the Y Py is any point here to the direct measure. Okay, and then of course that is a theorem or lemma. That's this is a measuring mapping because Y here has natural sigma algebra, and Py is a sigma algebra defined by Lovia. So you have to first to say that the direct mapping is a measuring mapping, and it takes a composition. Yeah, you got. So the many theorem in the Markov kernel you can prove very geometrically using the notion of the probabilistic mapping and the sigma algebra here. Okay, so that of course now I return back to the Friedrich example. So he considers sigma lambda is a sigma finite measure on X. Then Friedrich considers a group of on measurable one on mapping from X to X such that uh, the push forward, so the measure is dominated by lambda. Yeah, and if such a thing, then you can see that the push forward of the p lambda. P lambda is on the finite measure dominated by lambda. If you remember, is also in p lambda. Then it's not hard to see that the phi is a sufficient statistic and therefore sufficient probability morphism. You need to know that every statistic is a probability morphism. And then you can prove that any sufficient statistic is also sufficient probability morphism. And by theorem 1, then it preserves matrix. And then you get immediately corollary, and it's proved by Friedrich. The group G of the onto the measuring mapping onto mapping is isometric only on P lambda. It has a symmetry. Okay? So it has a very big group of isometry. Okay, now the last 5 minutes, I shall say very quickly about the diffeological grammar of inequality. So an estimator is a map from the X to P. That means X is on that our observation, how to say, sample, yeah? And from sample, you know what is a measure, X generated is a sample, right? So that is a, you have to design, how to say, experiment. So it's of course that's to find all this estimator very hard. So it's simpler to estimate of the coordinate of the phi psi, where psi is the px, and the phi is a mapping from the px to v. That v is some vector space. So that's a coordinate is nothing else as a function, yeah. Coordinate is usually coordinate function, but you can take the you take the first coordinate, 2 coordinate, but you can just coordinate that's combine in the function to the vector space. So that a var phi estimator is a composition of the map from px to phi to v. Actually, that's only after we on so that's the example. Var phi, that is I say consider the k is a symmetric position define the kernel, yeah, function, and v is the associated reproducing kernel in bed space. And then they noted kx is function on x defined by this way, and the kx is therefore that is the element of v. And then you consider px is based on probability limit measure. So you consider kernel mean embedding by. I'm sorry, that's for on the name here. And FSS, zero pupil from the Max Planck Institute in Germany. Yes, machine learning. Yeah, Schoenberg. Yeah. And there are all his collaborators from the Taiwan. Yeah. So they consider that the phi is a kx, they see x. Yeah, integration over x. And of course that's a that integral should be understood as Bochner integral. That means takes the value kx in the element in v, so the value function is in v, right? The space reproducing kernel Hilbert space. So the space v is the Hilbert space, right? So that's how to make they embed it from space of px to Hilbert space in this way. And so I call that means that's how to define the natural var phi map, yeah. So that's sometimes it's better to because once you have functions that mean take value in vector space, you can define a lot of things, yeah. For example, vector product or something like that. That's an I mean extra structure embedding. That's always the way mathematicians like to do. Yes, so that's in classical statistics, one consider only parameter estimation. And then they consider map from x to parameters s. But usually they only say that's a parameterization one-to-one, yeah. And in this case, parameter estimation equivalent to non-parametric estimation in sense of our definition. But in non-parametric statistics, they consider really non-parametric, yeah, estimation. And then this definition, I think that's a kind of non-parametric definition is the best one. And the notion of var-free estimation also occur in classical static under different name. For example, a substitution estimator, estimand, and every statistical book they have some. Not of course they have some many common, but some things they also have very name. So only yes. Now I consider to formulate the ecological statistical model. I need some notation. V prime is the ontological one of V with topological space. Phi L is a L phi, so we can consider that L component of the map phi, yeah. And L2 phi x by x is on map from the x to px. Remember that's the estimator. So that's the taking here that L coordinate of the var phi, yeah, is an L2 function. So I okay. So bye. And then it defines the var phi mean value is a mean value that usually you take the expectation, yeah. So that you have a lot of function here, but as a true point, you take the expectation. And now I identify V with some dual, double dual of V, right? And then you define that bias of estimator is a, you have the estimator is a true value of estimator. The thing that you can take the minus here only because the value of function in the vector space. So that is why you need to embed or to find some mapping to fixable. Otherwise, how you define the difference of the two values? Yeah, you can take the minus if the value is in vector space, right? So that's the bias of var-free estimator. So that's important. That's once the set is not linear, then you have to have embedded in some linear space. Yes, I mean that's the L. That's L is a V prime. Of course, that's you can write that L to phi. That's a yeah. So that yeah. Now the mean square error quadratic function is that usually you take the estimator to the true value at the C, and you take the mean value here, but L of A, so that you have the kind of the quadratic function. Usually you consider L, but you can consider L A as different L and A different element in the dual space. So now it defines a variant quadratic function is in usual way like that. That means that expectation of the phi L here minus here I am sorry that here that the bracket here, and then you can think that the variant quadratic function is you write in this way the plus so that's I mean that the variance quadratic function is a V and here is a n. So I'm sorry. So that here is a little bit confusing. I didn't note this thing and the ms square here mean square value must be equal variance plus the bias multiply bias. So I'm sorry that this part should be put here. And here's a variance function. So that's like in classical statistics, but here's a more interesting. That's consider this Riemann-based space, and usually you have the mean square error in for phi estimator in defined this way. So you take the norm, quadratic norm, and you take the expectation, and then you have the decomposition in this way, phi form, and now you can have the Cauchy basis, then you define in this term. Okay, then you define the completion of the tangent in terms of the Fisher metric in this way, and then you devise the inverse of Fisher metric on the completion in this way. Oh, yes, I have already run out of time, so it's defines the notion, and the function is locally bounded here because everything, if the finite dimension answer everything okay, if it's not finite dimension, it's not okay. And then you have the diffeological statistical grammar inequality like that. That's the difference of the variance to the minus of Fisher metric is a positive semi-definite quadratic form for any C. So that's the generalization of the Fisher metric grammar inequality on parameterized statistical model. Yeah, thank you.
We could answer question during. I have to install a Zoom. So if you, do you have questions? No.
Yeah.
The kernel mean embedding, so you showed, is it isometric embedding? So the embedding in the reproduced kernel Hurwitz space. Yes. Okay.
So they define the embedding of the space on probability measure on the space of the reproducing Heineken space, and they approve several estimator. I mean, that's a kind of doing machine learning on using that thing. Yeah. So I also have some reason. Yeah, as I consider also several infinite dimensional model.